Welcome to another video. In this video, we are going to discuss about velocity of sound in air using CRO method. Prerequisite of this video, waves and Lissajous pattern. When briefly, I am discussing what is Lissajous pattern. When our oscillator is under harmonic waves, the motion of that oscillator can be visualized by that assuming that this oscillator is moving around on a circle and the if we take projection of motion of that oscillator which is moving in a circle in any axis, either on x-axis or y-axis, this will give us the path traced by our oscillator. But what about when our oscillator is under two perpendicular harmonic waves? The motion of that oscillator under these two perpendicular harmonic waves can be the path traced by that oscillator can be visualized by Lissajous pattern. Lissajous pattern helps us to see what path is taken by our oscillator when it is imposed two perpendicular harmonic waves. So this is all about Lissajous pattern. What is content of this video? The content of this video is ways to measure velocity of sound, measurement by acoustic interferometer, theoretical approach, experiment. We have various ways to determine velocity of sound in air: by acoustic interferometer, by sonar, by resonance tube, and many more. In this video, we are going to cover measurement of velocity of sound by acoustic interferometer. So, what is acoustic interferometer? Acoustic interferometer is the device which measures the phase difference between two acoustic waves with the same frequency and different phases. By knowing the phase difference, we can know path difference, and by knowing path difference, we can know wavelength. And since we know the frequency of the wave, and by in this experiment we can know the wavelength. So by multiplying these two, we get velocity. How can we know the phase difference? When the two input of oscilloscope is introduced two harmonic waves, then the pattern which is obtained on the oscilloscope, which is Lissajous pattern, that show what will happen when our oscillator is imposed two perpendicular harmonic waves. By analyzing Lissajous pattern, we can know phase difference. By phase difference, we can know path difference, and by path difference, we can know wavelength. So, this is the target of this in this experiment. Theoretical approach. Let us assume that two harmonic waves moving in two perpendicular direction is given by these equation. Equation 1. In this equation, the amplitude of both waves are different, but frequency is same. These waves have phase difference phi. It is not necessary to be frequency same, but we are imposing two same frequency in this experiment to make our life easier. These equations basically show the trajectory of the oscillator. That is, at any time, what is the x component, what is the x and y position of the oscilloscope. But when after some mathematical manipulation, when we eliminate t from these two equations, we get the path which is traced by oscilloscope, which is this equation. This equation we can get by some simple mathematical manipulation. In this equation, we have eliminate time t. So this equation is in between x and y, which shows the path traversed by our oscillator. This equation seems similar to an ellipse, which shows what the interference of two oscillators which is perpendicular to each other. Equation 2 seems to be similar to that of an ellipse, signifying that interference of two oscillators perpendicular to each other which have the same frequency. So under this wave, in which manner are point to be moved? So are point to be moved along the ellipse. The shape of the position of the ellipse or R curve, which is given by this equation, depends upon the amplitude, which is x0 and y0, and the phase difference between these two waves according to this equation. So this figure graphically represent the formation of ellipse when phase difference is 45. It is not necessary that every phase difference gives an ellipse. What happened when we introduce phase difference of 45 degree? We will get ellipse. So this is the y-axis, this is time axis, this is x-axis, this is time axis. So the interference of these two, which is given in this by this figure, shows. So I am explaining how this is happening. We see that this wave and this wave. So this wave have phase difference of 45 degrees since this started from this point. Now at time t equals to 0, the position y component of the oscillator is at origin, but x component is at this negative x-axis. So combination of these two gives this y component 0 and x component is this. And after some time, after some equal time, that is which is given by position 2 here and here, we get the combination of these two, that is x maximum in the negative direction and y is this much. When some time passed, we get 0.3, which is corresponding to maximum in the y-axis, y direction, and this much in the x direction. The superposition of these is given by this maximum in y direction and this much in x direction. And similarly for 4, this is unequal. This 4 position and this 4th position is at same time, and the combination of these two is this. 5th is this, 6th is this, 7th is this, and similarly 8th is this. So we get ellipse. Using similar approach, we can easily see the Lissajous pattern for 0 degree, 45 degree, 90 degree, 135 degree, and 180 degree as shown in the figure. For 0 degree phase difference, we get a straight line making 45 degree with x-axis. For 45 degree phase difference, we get ellipse. If you are thinking that this ellipse is generated by phase difference of 45 degree, this ellipse is generated also when the phase difference is 45 degree. So orientation is both different, but because here we have sine wave, or here this is made by cosine wave. But eventually we will get this when we have cos wave. This is for 90 degree, this is for 135 degree, this is for 180 degree. Sorry, I have not keep this slide in proper manner. I have take this here. Anyway, and the experiment, the main part, which is experiment. The objective of this experiment is to determine the velocity of sound in air using CRO method. Apparatus, audios. For this experiment we need an audio oscillator, impedance matching transformer, 2 loudspeaker, and CRO. So we know audio oscillator will generate audio wave. Impedance matching transformer is used in this experiment to get maximum output at CRO and 1 loudspeaker. When we will proceed ahead, you will understand what we will use these apparatus. So what is processor? The processor contains 2 parts: the setup of our apparatus and the measurement. This is the view of experimental setup. This is close view, this is far view. This is audio oscillator, this is CRO, this is loudspeaker, this is second loudspeaker, this is impedance matching transformer, this is also impedance matching transformer. This loudspeaker is used, I don't know in how manner, but it is used as a microphone to get audio frequency. So how we have set up an experiment? You can read this. This PPT is given in the description box below. I am explaining this. So audio oscillator have 2 output. One output is directly connected to the x-axis, x input of the CRO, and the y and second output of the audio oscillator is connected to this impedance matching transformer. So by the use of this, I don't know, but this is used, so we get maximum output at this loudspeaker by maximum power transfer theorem. And so this loudspeaker will generate audio wave which travels through air and received by this loudspeaker, which is used as microphone, and this will convert it into electrical signal. And here we have used impedance matching transformer, which is connected through y input of CRO. So we get maximum y input. Now, since the wave which is going through x input and the wave is going through the y input, these two waves have phase path difference due to when air is goes through, sound is goes through to CRO by y input, they have, due to sound is going an extra path in the air, so due to this they will get the x and y input have path difference. This path difference can be changed by shifting these two in to and fro. So we get various types of Lisa-Jones pattern. By analyzing these, we get wavelength. This is far view. We can move this to and fro. So this is the experimental setup. What is the procedure for measurement? We will turn off time-based control of, I don't know why, of CRO. I don't know why it is turned off, but it is written in the manual. We will switch off audio frequency oscillator and set it on various frequency 1.45 kilohertz, 2 kilohertz and 2.5 kilohertz. First we will take reading by 1.45 kilohertz, then 2, then 2.5 kilohertz. We will move microphone very slowly away from the loudspeaker. Curve 1. We will keep this microphone as near as possible to this loudspeaker and we will move this microphone further away from this loudspeaker. Now we will note down all the position from the from the loudspeaker, not on this scale. This is stand having scale. So we will note down all the position of this microphone by using a scale which is mounted in this rod, where on the CRO screen these type of traces obtained, starting from positive sloped straight line, then ellipse, then circle, then 90 degree or rotated ellipse, then negative sloped straight line, like this. And finally we will move our microphone at this much, so we get again this positive sloped straight line. These traces on CRO screen is corresponding to phase difference 0, pi by 4, pi by 2, 3 pi by 4, pi and 2 pi, as I explained previously, between sound signal. The phase difference phi is produced by extra path traversed in air by the sound wave, which are fed to the X and Y plate of the CRO. As I mentioned, the phase difference or the part difference is produced due to extra path which is traversed in the air by sound wave. Thus, from this data we calculate wavelength of the sound. This is observation. This observation is taken when the lab temperature is 20 degree. So we get this straight line, positive sloped straight line, which is corresponding to part difference 0 degree, as I explained. Then ellipse, which is corresponding to part difference pi by 4. Then circle, which is corresponding to circle. Then pi by 2, which is corresponding to circle. Then 3 pi by 4, which is corresponding to 90 degree oriented rotated ellipse. Then straight line, which is 90 degree rotated straight line from this, and then again same pattern which is obtained when when the frequency is 1.45 kilohertz, we get the position of microphone or speaker which is used as microphone is this. For 2 is this, for 2.5 this. Now this is the table, calculation table. This is observation table, this is calculation table. So this is the frequency, this is the phase difference. This phase difference is corresponding to part difference. This is the position here. Since our scale is a meter scale, the accuracy is big. I can measure the smallest will be the value will with the accuracy. So this reading is under this uncertainty, plus minus 0.01 centimeter. So actual part difference in the centimeter will be given by this. Since we know that after 2 pi phase difference, 2 pi phase difference is corresponding to 0 phase difference. So since we know that waves in sinusoidal, so after some time these pattern will repeated. So this is not the same as the part difference is 0, since we know that after some time the part difference will again goes to 0. After some distance part difference will again goes to 0. After some difference again part difference goes to 0. sine function have time period. So after some distance the path difference will again goes to 0. So actual path difference is obtained by subtracting the position of 0 phase difference of pi by 4 all the phase difference from 0 phase difference. So the actual path difference for pi by 2 phase difference is getting by subtracting these value from this, for this value from this, for this value from this, for this value from this, from this, for this value from this. If we again taken away the microphone from this position, we will get again the after some distance the path Lissajous pattern which is corresponding to phase difference pi by 4, but the position on the scale is not corresponding to path difference in the centimeter. We will get actual position by when we subtract those value which will get on the scale by 36.3 centimeters. So this is the concept why we are subtracting this. Similarly for this and similarly for 2.5. So what will be the wavelength? Since if we all add these data, so if we all these part difference, this all the part difference will corresponding to 9 by 4 lambda. So addition of this is corresponding to 9 by 4 lambda. So we want to get lambda, so we will divide by 9 inverse of 9 by 4, that is 4 by 9. So we have summed all these and multiplied by 4 by 9 for this and this. How I get this type of this percentage accuracy? Since relative accuracy, percentage accuracy of this part difference is plus minus 0.1 upon 3 into 100, and for this plus minus 0.1 upon 6 into 100, and for plus minus 0.1 upon 9.1 into 100. Similarly this and this. So for all these we get percentage accuracy, and I have taken average, since we have said that we take maximum observation and then take average, which will correspond to more accurate data. So I think this is the right way to get percentage accuracy for these four wavelengths. So after getting wavelength, we will multiply. I know you are thinking why here is not accuracy. I don't know by what accuracy the audio oscillator is generating audio wave. So I have not considered in the accuracy. So after multiplying this frequency with this wavelength, we get velocity of sound in air, which is this and this. This is on 20 degree centigrade. This is by taking average, we will get this average value of velocity of sound in air, which is 352.6 meter per second with the accuracy of 1.98%. This is the frequency of sound in air when the temperature is 20 degree centigrade and the pressure is 1 atm. So actually this is not on the wrong place, this is on the right place, since we have get that velocity of sound at which temperature, which is on the lab. For my case, this is 20 degree centigrade. So we have measured the velocity of sound at 20 degree centigrade. But for comparison, we have to compare it from that data which is available to us, which is velocity of sound at 0 degree centigrade and at STP, that is 1 atm pressure and 0 degrees temperature. So we have used that equation, which is Newton-Laplace equation used for ideal gas. We have considered that our air is ideal or approximately near to ideal. So this is the dependence of velocity of sound at temperature, which is this is proportional to inversely, which is proportional, not inversely, which is proportional to square root of temperature. So here T is in Kelvin. So after some manipulation, we will get the velocity of sound at 0 degree temperature, this much. Here this T is in centigrade in terms of velocity at any temperature, and temperature is taken at centigrade. I think you can all get this expression from this expression. So now calculation. We have get the velocity of sound in air at 20 degrees centigrade is this much with accuracy with this. So from this formula we will get the velocity of sound at 0 degree centigrade. So we have put all the data, and we have get this much velocity of sound in air at 0 degrees. We will get if the temperature is 0 degrees centigrade. This. So actual value is, but actual value is 346 meter per second. So what is the error of this experiment? So error in this experiment is relative error, that is difference of actual value and experimental value upon actual value into 100. This is the error, which is 1.6%. Well, we calculate error by taking difference of experimental data and actual data, difference, not subtracting difference, and by dividing that with actual value. Whether actual value is larger or experimental is larger, we will always divide this with actual value. So what this is the result. The velocity of sound, which is measured in experiment at 0 degree centigrade, is this, but actual value is this, so error is 1.6%. Conclusion. We conclude that Lissajous pattern can be used to determine the wavelength of sound more theoretically, as I have mentioned, explained in theoretical approach as well as experimentally, as I have explained in experimental part. So Lissajous pattern can be used to determine the wavelength. Also we see that the approach provides us with fairly accurate results, which are in good agreement with the available data. That is, we have calculated with only 1.6% error. Thank you.